Okay, so the expectations on this are that you would write, for a warm-up, something like, I believe a G series will converge if it has R between -1 and 1. See what I mean? G stands for what? Geometric. Yeah. Oh, does anyone know the abbreviation for R is between -1 and 1?
Absolute value R is less than or equal to 1.
Absolute value R is less than 1. Yeah, so you can write it this way or this way, same thing. Don't put the equals on there because that will actually diverge. So yeah, like on the right, you could put G series with absolute value R greater than or equal to 1. Diverge. So that's how I want you to fill this out. Okay, don't put specific problems in there. Just types of series that converge and diverge. This is a very common question to ask somebody, like what kinds of series converge. You can also just go on the internet and ask what kinds of series converge. Just Google that question. But anyway, did you guys find anything else in the notes that would converge?
The P series with the power greater than 1.
Yes, P series
Telescoping.
with R is greater than 1.
Is that called R, that low power?
Oh, it's actually called P, sorry. So P is greater than 1, good. G series, I'm sorry, P series with R is less than or equal to 1 would be a divergent. So what in the world is the difference between a P series and a G series? Let's go over that real quick. So it's actually really easy to understand if you think of it this way. Whenever you have a number to a variable, that's a G series. Okay? And whenever you have a variable to a number, or more specifically 1 over a variable to a number, that's a P series. All right? So in both cases, the number is, of course, a constant number, and that number will tell us if it's going to converge or not. For example, the first one, if the number in the parentheses is between -1 and 1, converge. If it's 1 or larger, or -1 and below, diverge every time. If it's 1 over variable, and by variable in this class, in this chapter, we mean n, okay? So if it's 1 over n here, and there's a number there, when the number is greater than 1, it converges. Less than or equal to 1 diverges. So they're kind of opposites, really. They're opposite in their form, and they're opposite in their result. Okay? That should not say P series with R is less than or equal to 1. It should say P series with P is less than or equal to 1. Sorry, I did that same mistake twice there. Sorry. Okay, and then you mentioned telescoping series, Hunter. Good. And I'm thinking about if all telescoping series converge, I'm actually thinking maybe that's not quite true. But certain telescoping ones, like this one we did the other day, it was awful. I think it was n squared minus 1 on the bottom. This one was a telescoping. It's telescoping because when you start writing out the terms, you realize a bunch of stuff is canceling out. But we had to do partial fractions first. What a nightmare. Okay. Also, the first day, didn't I give you guys a little test to show that something's divergent?
Yeah.
Okay. So aren't there certain series that are just definitely divergent? Look back at day 1 notes. Look at the nth term divergence test. Huh?
Just ones that fail that test? Or?
Yes. But look and see what is that test requiring us. That's right. So any series whose summand does not have a limit of 0 as n goes to infinity. What's a summand? Well, you have integrand and radicand and summand. Summand is the part after the sigma. So if the summand doesn't have a limit specifically of 0, then the series will be forced to diverge. That's a good little thing to know. And then yesterday we did integration, right? So how can you tell if a series is going to converge or diverge using integration? Then so does the series. If the integral diverges, so does the series. Yeah, so we can just write that in our last row here. Give myself a little more space. Any qualified series, so any positive, decreasing, continuous summand with an improper integral that converges. Will be a series that converges. And then the opposite is true. Any positive, decreasing, continuous summand with an improper integral that diverges. Will be a series that diverges. So basically we can tell if a series will converge by checking its integral. That says any positive, decreasing, continuous summand. It should say any series that has a positive, decreasing, continuous summand with an improper integral that diverges. Okay, so that will help you with your little quiz, okay? This way you can quickly reference this. Some of my quiz questions are simpler than they look, okay? I'm just asking you, do you think this converges? I'm not asking you to find the convergence value. Just see if you recognize the type of series. Maybe it's a P series. Just say, yeah, Mr. Short, it's a P series. P is greater than 1, P is 2. Yeah, it converges. Don't try to find the convergence value, okay? Let me give you the quiz. It's supposed to be a 10-minute quiz. Pause my recording. Okay, so I just started the recording again. What are the tests we've learned so far? Let's fill in the blanks here. Okay, so first one is actually not the first one we learned, but the one we learned most recently was the integral test. And there are rules about the integral test. If you want to use the integral test, you need to make sure that you're dealing with a positive, decreasing, and continuous summand. Okay? So you may not use the integral test on a problem like this. Or something. Well, for one reason, it's kind of hard to integrate sine x over x squared. Good luck with it. But the real reason is because technically sine n goes up and down, and this says decreasing. So this isn't even, you wouldn't even use the integral test on this problem. All right? Same thing with anything that has this in it, guys. You guys recognize this little -1 to the end? Maybe you've seen that before. This thing's extremely bottom heavy. So I'll bet it converges. I'll bet you $50 it converges. But I shouldn't bet. But what I'm saying is it definitely converges, but I'm not allowed to use the integral test to show that. You see, I can't do that. And the reason, there's actually two reasons why. One, -1 to the x is totally meaningless. Think about it. If this was -1 to the x and you're trying to set an integral, if x was a half, it'd be I square root of -1. If x is a third, it's like the cube root of -1, which is -1. So it doesn't even always exist. -1 of x doesn't always even exist for all real numbers. So this is just not a good candidate for the integral test. It's not even a continuous function. And what's worse is it goes under the x-axis quite frequently. So you're not supposed to use it. It's not always positive, see? So don't use the integral test like as a go-to test. You got to make sure that these three conditions are met, right? So just be careful with things you're given to use them at the right times. What you're supposed to do to actually perform the integral test is you're supposed to write the improper integral is what you did on the worksheet. Write the improper integral whose integrand is the sum end of that series. Evaluate the integral. If the integral converges, then so does the series. If the integral diverges, then so does the series. It's a great test if you use it in context. Finding the partial sum formula, that requires a lot of work, a lot of paper, a lot of free time, and a lot of false starts. Okay? This is what we did with that telescoping problem. If you remember from day one, when we tried to do this problem here, we had to break it into partial fractions. We wrote out the first 7 terms. We wrote out the last few terms before the nth partial sum. We tried to look for what canceled. What a pain. Finally, we created a little formula from the survivors and finally took the limit. So the process is just that. You write out the first few terms, or first several terms is even better. Then you write out the first few partial sums, and perhaps the last few partial sums that lead up to the nth partial sum. You look for a pattern. You try to create a recursive, not a recursive rule, but an explicit rule for S sub n, and then you find the limit of S sub n as n goes to infinity. This is a horrible process. It actually will work on any problem, no matter what kind of series it is, but it's so hard, it's not our go-to, and sometimes almost impossible. Okay, so the third technique is what we're going to talk about today. If you had to pick one of these from this table and describe today's lesson with it, it would be this third box. So this third box says, just check to see if it's one you've studied before. Okay? So is it a G series? Maybe it's a P series. Maybe it's a telescoping problem. Why would you redo the whole problem if you already have done a G series or P series in the past? So on my quiz, it was not my intention for you to solve the problems, all of them. On the problem, for example, that said, let me look at my quiz again. There's one on here that just simply says, does 1 over n cubed converge or diverge? The answer is it converges. It's a P series with P equals 3. That's all I needed from you. How many of you actually answered one of the quiz questions today as, the series converges. It's a P equals 3 P series. Did anyone write that? That's exactly what I was looking for. Okay? Good job. But to do that, you have to have some prior knowledge, right? That's the tool you need. And you have to ask yourself the same questions every time. Is this a P series? Is it a G series? Maybe that's all it is, just a P or G series. All right. By the way, there's a difference, another difference between P and G series. With G series, I might ask you to find the actual convergence value, because I gave you a formula, A1 over 1 minus R. If it's a P series, I probably will not ask you for the convergence value because, well, there are formulas, but every one of them is different, which makes it a pain. So I'll just ask you, does it converge? Let's go down to here. Today we're going to extend our abilities by learning to determine whether a series converges or diverges by comparing it to another more familiar and simpler series. So for that reason, we call these comparison tests, and there are 2 of them. There's the direct comparison test, which I'll call the DCT, and the limit comparison test, which is called the LCT. And today, all I hope to do is to get to the direct comparison test, maybe do 4 or 5 examples for you, and show you how to write your answers concisely. Okay? All right, so typically what you need on these problems is a little background knowledge of other series, which is what that table at the top is for, okay? So this table right here, guys, is your friend. Okay, keep your eye on that as we do our examples, even though it's on the other side of the page.
Is that how you do it? You have like stuff written down and then you have another copy?
Yeah, I have my answer key at the top. Okay, so let's go on and look at our first set of examples, page 2 there. The direct comparison test. Oh, let me go over this first. You have to kind of fill this table in first. Before you can use the test, conditions prior to using the test. The 2 series must be different, okay? You can't compare 2 things that are the same. So you have to make sure you're picking 2 different series, and the sum end of these 2 series must yield positive results. please do not use a direct comparison test on a problem like this one. This is not a good candidate for the comparison test. It has some negative terms in it. In fact, every other term is negative. So please do not use a comparison test with that problem. Let's go to the right side, how to do the test.
Wait, Mr.
Yeah, question?
What do you mean the summand of the two series must yield positive results?
So basically, let's say you're doing this problem, and you decide you wanted to compare that to this problem.
Right.
We would only do this sort of comparison if these give positive results. So these are the summands.
Always positive?
Or at least after a certain n, things begin to be positive from that point on. So it is okay for the first couple terms to be negative, but then it needs to take on a positive behavior and stay positive from that point on.
Okay.
So like after n equals 4, it needs to produce positive fractions from that point on. Okay? So that's when you're allowed to use the DCT.
Okay.
Thanks for asking. Okay, so let's fill in the blanks on the right. You scroll down a little bit and zoom out a little bit. How to do the test. You're going to show that the series A converges by showing that A is less than B. So A is less than or equal to Bn, where Bn is a series you already know converges. So try to show me that it's less than something convergent. We've done this before. It's with integrals anyway. Show that this, the other way is show that the series A diverges by showing that it is greater than B, where B is something you know diverges. So if you can show me that this new series you're studying is less than something convergent, then it must converge. Or show me that it's something that's greater than something divergent, well then it's going to diverge. Okay? All right. The hardest part is picking a good B sub n. So some hints for picking a valid second series B sub n would be, here are my hints to you anyway. Make sure that you know about B sub n. So don't pick a series you've never studied before and try to compare it to another series you've never studied before. One of your series at least should be a familiar, comfortable series. And then when you begin your testing, you need to check, if you suspect convergence, you need to show and check, double check, that it is term by term greater than the series that you believe converges. Or if you suspect divergence, you want to show that it is term by term. The one you pick will be term by term less than the sequence you're studying. This will all be very clear in a minute. Okay? The goal is to simply show that something is less than finite, which makes it finite, or more than infinite, which makes it infinite. It's that simple. Okay? Do you guys remember when we tried to create an integral that was similar to another integral, and we tried to do that? We tried to show that the new one we picked was actually convergent. We did that on our last test, the last page, last problem. Do you remember? So that is the same idea, only this is a little easier than that. This is actually a little bit easier than that. All right, so let me give myself a little more space here. What would I use to compare, for example, 1? Well, look at this series. This resembles 1 over 2 to the n, at least in its structure, right? So this is a good series to pick. It resembles the one we're working on. Can I move this? Yeah, you move over here. Okay, thank you. I talk to my equations sometimes, or my expressions. I'm picking this for 2 reasons. One, it's simpler. And for the second reason, it resembles the one I've been given. Also, it's one I've studied before. This is just a what? What kind of series is this thing? Maybe it'd help you if I wrote it like this. If I write it as 1/2 to the n, maybe it's really obvious to you. This is a G series. It's a number with an n power. So it is a G series. What is the R value? R is a half. Is that between -1 and 1? Great. Okay, so this is a convergent G-series, you could say. So this is a series that I'm comfortable with, and it resembles the problem I've been given. Okay, so I'm going to test against or compare to this one. All right. So here's my sentence. I'm going to put the series I've been given converges because it is term by term less than, it is term by term less than the series n equals 1 to infinity 1 over 2 to the n, which is a divergent, or which is a convergent G-series. All I need is this blue sentence. I don't need any work, but your blue sentence must be true. Okay, let's see if my statement is true. Is it true that 1 over 3 plus 2 to the n is term by term smaller than 1 over 2 to the n? Yeah. It's true. This always will give you a smaller fraction than this will, because it's got an extra 3 added on the bottom. So I don't need you to do a lot of complicated, like show me the first 10 terms or any of that, but your statement needs to be fully true, and I can accept it. You don't even have to write the red, just write that blue. If it's true, I'll give you the credit. It's hard to fake this anyway, so if you wrote that sentence, you must have understood it. Don't forget to write which is a convergent G-series. Why do we say that was a convergent G-series? Because the R was, yeah. Okay, so you don't even have to justify that either, okay? Just tell me it's a convergent G-series, and I'll believe you. Let's look at example 2. Okay, see on this next problem, I would not say it resembles 1 over 2 to the n, but I would say it resembles what? 1 over n squared, correct. So I'm just thinking that right off the bat. And so I'm going to start my blue sentence right now. I'm just going to jump in. Oh, by the way, 1 over n squared, is that a convergent or a divergent? This is a P series. It's convergent. The reason is this graph, 1 over x squared, attacks the x-axis so quickly, it pinches off a nice finite area, okay? So it swiftly attacks the x-axis, and it makes a sliver of area that's actually measurable, if you could say it that way. Everyone understand that we're going to compare it to this just because it looks kind of like it? All right, we're ready to write our sentence. Hunter, do you have a question?
Yeah, I want to pause it
Oh,
though.
that's very interesting. Okay, so we're going to compare it to this. We could use integral test, but we're doing DCT today. So you would just simply start in on your blue sentence and say, I believe that this converges because it is term by term less than this series, which is a convergent P series. So it's almost exactly the same sentence as example 1.
Couldn't you say it's term by term less than the convergent P series?
That's what I said, yeah. Term by term less than the convergent P series, 1 over n squared. Oh, you want to switch the sentence around a little bit?
Yeah, it just
You can do
makes
that.
it more efficient.
Sure. Yeah, you could put the which is a
I don't
convergent.
know why.
You could put the convergent P series part before the sigma. I'm going to record 2 more examples, okay? And then I got to race off to a meeting, so I'm still talking. If you guys could just keep it quiet on your way out. I actually have to record these before I go to my meeting. All right, so for our third example, I believe this would diverge because it looks like 1 over n. looks kind of like 1 over n. So I'm going to write this diverges because it is term by term greater than the series 1 over n, or n equals 3 to infinity, which is related to the harmonic series. The harmonic series is 1 over n. In fact, it's actually just the third, fourth, fifth, sixth, seventh, eighth, etc. terms of the harmonic series. Okay, so this brings up an interesting question. This is not starting at 1. It starts at 3. So you might say, well, that's not valid, Mr. Shore. You cannot compare this to the harmonic series. It's not the same series. But listen, the harmonic series was the one that starts with a 1 at the bottom. And then there's a 1 over n here. And this, remember, goes all the way to infinity. So the fact that it's missing the first two terms, which are specifically the terms 1 over 1 and 1 over 2, the fact that it starts with 1/3 plus 1/4, etc., if all of these numbers add up to infinity, taking off the two blue numbers is not going to change that fact, right? So the harmonic series will diverge even if you take away the first 1,000 terms. It would still diverge, you see. So I'm going to put it's related to the harmonic series, which is divergent. It's not exactly the harmonic series, but it should diverge the way the harmonic does. And then my last example today, last two examples actually. For this one, I would probably want to compare it to 1 over rad n. So I'm going to start my sentence like that, and I'll show you why that's not quite the right thing to write. So if I wrote this, I might say this is divergent because it is term by term greater than sigma n equals 1 to infinity 1 over. Now I'd love to just put rad in here, but this sentence isn't quite true. Why? Because 1 over 3 plus root n is actually term by term smaller than 1 over rad n. The sentence isn't true, you see. So how am I going to fix this? Well, it turns out that this was just a bad choice. It was a bad choice for a comparison series. What you need to do is pick a different known divergent series. So I'm going to actually scribble out the rad n, and I'm just going to put n instead, right here. Now the statement is more true. 1 over 3 plus root n does give you bigger fractions in general than 1 over n does. Let me show you. So first is 1 over 3 plus root 1, 1 over 3 plus root 2, 1 over 3 plus root 3, 1 over 3 plus root 4, 1 over 3 plus root 5, 1 over 3 plus root 6, 1 over 3 plus root 7, 1 over 3 plus root 8, 1 over 3 plus root 9, 1 over 3 plus root 10. So I'm writing out the first 10 terms to show you something interesting. The series 1 over n is just 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, 1 over 10. This statement is, the sentence I wrote is true. Okay, it is true. The sentence I wrote is true. But not until you reach the 9th term. Okay? Starting with the 9th term, actually after the 9th term, this is now a true statement. So actually the series is term by term less for the first 8 terms, then these two are equal, but then thereafter the statement is true. So I just have to qualify that. I just need to write one more small thing. after n equals 9. Or some people write for n's greater than 9. This makes the sentence completely true, and that's what you would need to do. You need to make a sentence, of course, that's completely true. So this one's a little harder, isn't it? A little harder to find. You could have maybe just done this by the integral test, you know. JCT is not always the best go-to test. And then more tests to come. I think I'll save the last one for a warm-up problem, and probably won't even record it, but you have it there in the notes if you want to try it tonight.